All right, so let's go through this equation sheet. We've got distance equals rate times time. We've got wavelength times frequency equals the velocity of a wave. We've got, if you want to know how fast something is going, if it starts with an initial velocity and then accelerates at a constant rate for a certain time, that's a linear graph there. And that'll tell you how fast it's going at the end. We've also got, in the same situation, if you want to know instead how fast it's going, if you want to know how far it goes after a certain amount of acceleration, depends on its initial velocity and the acceleration it undergoes, and then how long it undergoes it for. You put in that, and then you get how far you go, and that's a curve that looks parabolic like that. Okay, and then you have, you want to know how fast you're going given an initial velocity and then an acceleration over a distance. There's no time in that equation. So those are your kinematics equations. There's similar ones for angular stuff, but we don't have to worry about that. You've got your F equals ma here. You've got the force of gravity is also called the weight, and that equals your mass times gravity, or whatever the object is. If you've got an object sitting there, or in free fall, the force of gravity is mass times g. And in this case, mg equals ma. You get acceleration 9.8 meters per second squared. Ta-da! Okay, you've got the normal force is in general mg cosine theta. So if it's at some angle like this, the normal force, you're going to have the weight down, and the normal force in general is the component w cosine theta. Unless it's flat, then it's just w mg. The force of friction is mu k times the normal force. So you calculate what the normal force is. Depends on how heavy the object is in contact with whatever it's in contact with. And there's the kinetic version and the static version. So if you're moving, you use the kinetic version. If you're static, you use the static version. And that's one of the sum of the forces things. So these forces get summed up. Force on a spring, another one that could go on the side of the equation, F equals ma. Minus kx, spring constant, times how far the spring is stretched. The centripetal force, if you got something accelerating, in a circle, the only way to keep it on a circle is if you constantly pull it back to the center, and you have to keep pulling it with mv squared over r amount of force. That's the mass of the object times how fast it's going times the radius of the curvature. So that dictates the tension in the rope, for example, if you're swinging something around your head. This is the force due to gravity, mass 1 times mass 2 divided by the distance between them squared. This is what g is that goes in that equation. It's just you got two masses separated by a distance r, and that will tell you the force between them. This is the F equals ma, but written in terms of change in momentum over change in t. Delta v over delta t is acceleration, so m times delta v over delta t is the same thing as momentum, because momentum is mv, and then angular momentum is I omega. So if something's rotating with a certain moment of inertia at a certain angular velocity, omega, then it has momentum. If you add up all the forces on an object, you get an angular rotation if it's not balanced, and that gives you the net torque gives you acceleration, I alpha. Otherwise, an individual torque that goes on the left side of that equation can be found by taking the distance that the torque is being applied times the force that's applying it. The distance of force is being applied from an axis of rotation. So if something's going to rotate, and then you're going to take that force times the distance, and then it's the component of the force, sine theta, that gives you the amount of torque. Okay, v is omega r. This relates the linear tangential velocity to the rotational velocity. It depends on r. So you get omega, which is independent of r, and then the tangential velocity will be dependent on r. The further away you are, the faster your v, the higher your v is. But your omega is constant. Okay, then you got omega is equal to 2 pi f, 2 pi times the frequency, and then 2 pi over t. So you have a cosine omega t plus phi, some equation like that. That omega is here. It's related to the frequency and the period with those two equations. W is fx cosine theta, so this is work is force times distance. If your force, if your distance, you're going to move this way, but your force is at an angle, you want the component cosine of theta times the force times the distance that you move. That's the amount of work. So it's in general force times distance, but usually the force is at some angle, so you want the component that's along the motion. Any object that has a velocity is going to have kinetic energy, 1/2 mv squared. Any object that is up in the air is going to have some potential energy, mgh. You can convert them into each other. Drop something, for example, it'll speed up, and then you set them equal to each other. If you load a spring up, distance x, depending on the spring constant k, 1/2 kx squared is going to give you the energy stored in the spring. Your total energy then is in general the sum of all the energies, all the kinetic energies, all the different potential energies. So if you've got an object flying around and it's up in the air, then you're going to do 1/2 mv squared plus mgh to calculate its total energy. This is your, you don't have to worry about that equation, that's your force per area is equal to, this is the elastic stretching deformation equation. Density is mass over volume. Pressure is force over area. Pressure is also equal to rho gh plus your atmospheric pressure, or whatever your initial pressure is. Remember, that's gauge pressure, and this whole thing is absolute pressure. The buoyant force is equal to the mass of the fluid times the weight of the fluid, which is the mass of the fluid times gravity. The mass of the fluid is density times volume. If we solve that for mass, m equals rho v. So that will give us the force. If we have a net force, if our buoyant force is not strong enough to keep the object from floating away, so in other words, if we have the buoyant force up and the weight down, and if our buoyant force, sorry, did I say not strong enough? I said if it's strong enough to counteract the weight of the object, then the buoyant force minus the weight is going to equal, if we go back to this equation, F equals ma. On the left-hand side, we have the sum of the forces. We have to add the buoyant force and we have to add the weight together, and they're opposite, so they cancel out. So, they're negative opposite each other. So we have FB minus W, and that should give you an acceleration. You can solve for the acceleration if something is not buoyant, neutrally buoyant. This is the flow rate equation, that the flow rate through one area is equal to the flow rate through the other. The density, if it's water in one area and water in the other area, those are usually the same, so that cancels out. So you have Q1 equals Q2, area 1 times V1 equals area 2 times area 2. That's Bernoulli's equation. That relates the pressure at some point in a fluid to its kinetic energy and its potential energy. At some point, all that adds up. That's the total energy in a fluid at some point, and that has to equal the pressure and kinetic energy at another point too. Okay, the speed of a wave depends on the tension in the rope and the mass density of the rope. The period of something is 2 pi times the square root of m over k, a simple harmonic oscillator. A simple pendulum, the period only depends on the length. Okay, so you've got your period and your pendulum here. You can relate omega and the period this way, so be able to do that. Then you have the fundamental frequencies of either a tube that's open at both ends or a tube that's open at one end and closed at the other. You know the difference. Then you have the way to calculate decibels, the intensity of a wave. Now we have our Doppler shift. The frequency we would perceive is equal to the initial frequency times 1, either plus or minus the velocity of the observer divided by the speed of sound. Generally, if it's coming towards you, you're going to have a plus here, and your frequency will be increased, and you'll hear a higher pitch. Okay, 2 pi radians equals 360 degrees. The circumference of a circle is 2 pi r. The density of water is 1,000 kilograms per meter cubed. You got some other generic conversion factors here. And that's it. Okay, see you guys later. Bye.